Yeah, so firstly, thank you very much for the invitation to speak. I've really enjoyed the workshop so far, and yeah, looking forward to the rest of my time in Sydney. Yes, I'll be talking about Sparse Blossom, which is this is joint work with Craig Gidney, and the bulk of this was done at an internship with Google last summer. Okay, so I'll start with some motivation and background on sort of why we care about fast decoders. I'll then sort of give an overview of the minimum weight perfect matching decoder, or the problem. I'll then sort of give an overview of Edmonds Blossom algorithm, and then our approach, our kind of variation of it, the Sparse Blossom algorithm. Talk a bit about sort of some of the optimizations and how we made it this fast, and then conclude. Okay, so why do we need fast error correction tools or decoders? So one reason is we sort of want real-time decoding. So a large fault-tolerant quantum computer will generate around sort of 3 terabytes of data per second, or around sort of 0.5% of global internet bandwidth. And all of this needs to be processed in real time. In particular, we need to match the throughput of the device to prevent the syndrome data backlog increasing exponentially in the T-gate depth. So this is an observation made by Barbara Terhal. And so at the point at which you're, say, implementing some logical T-gate, this logical measurement here has to be corrected to prevent applying a Clifford error, which can't be sort of propagated through like a Pauli frame. So you have to keep up with the throughput at least, not necessarily the latency, but the throughput has to be keep up with the device. And in superconducting quantum computers are fast. So each error correction cycle takes sort of less than 1 microsecond. And so a reasonable goal for real-time decoding might be that we want to decode, say, a distance 30 surface code in 1 microsecond per round, let's say 0.1% circuit level noise. Another reason is that you might want a fast decoder is for error correction simulations, as many here will be familiar with. So direct Monte Carlo sampling is very expensive, and so logical error rates should be very rare by definition. So if you actually want to assess the performance of some error correcting code, you have to sort of estimate the likelihood of very rare events. And that often means you have to sample hundreds of millions of shots from huge error correction circuits to estimate thresholds and overheads of error correction protocols. So for example, just like one data point on this graph from a recent sort of benchmarking paper requires probably more than 10 to the 8 samples from some very large circuits. And so doing these sort of analyses in a reasonable time requires fast tools, simulators, and decoders. So in this work, we introduce a new implementation of the minimum weight perfect matching decoder. And it can decode both X and Z bases of a distance 17 surface code in 1 microsecond per round on a single core at 0.1% circuit level noise. It's open source. So some of you may have already been using it. So it's released in the second version of PyMatching package. So feel free to upgrade if you have version 1. It's got roughly linear expected runtime, and it's sort of 1,000 times faster than the previous version of the library, and around 100,000 times faster than NetworkX. And the paper's not yet on archive, but will be soon. Yes, so some background now. So what are detectors and observables? So a detector is a parity of measurement outcomes that are deterministic if no errors have occurred. And a detection event is a detector outcome that is flipped relative to its expected value. So for example, a detector in a surface code memory experiment is just the parity of consecutive stabilizer measurements. And generally, each error mechanism will cause a small constant number of detection events. And a logical observable is also a parity of measurement outcomes, but it corresponds to the measurement of a logical Pauli operator. So we want to use the detector outcomes to protect and correct the measurement of these logical observables. And so, yeah. So using this kind of annotated circuits, we can construct a detector graph. And so for some error correcting codes, such as the surface code or honeycomb codes or subsystem surface codes, hyperbolic codes, it's sufficient to consider only the error mechanisms that cause either 1 or 2 detection events. And if that's the case, we can define a detector graph. So we have a node for each detector, and then an edge for every error mechanism. And so these blue stars here are sort of correspond to detection events. And then, yeah, so the endpoints of the edge are the detectors that an error mechanism flips. And then for each edge, we can assign a weight log 1 minus p over p. And so in the surface code, for example, the X-type and the Z-type errors are both graph-like, and so we don't need to handle Y errors separately in order to correct up to the code distance. We might want to, but we don't need to consider them at all to decode up to distance. Okay, so what's the minimum weight perfect matching decoder? So it finds the most probable graph-like physical error. So considering only the error mechanisms that fit one or two detectors, it finds the most probable sort of error. And so it's not optimal because a maximum likelihood decoder would find the most probable logical error considering all error mechanisms. But it's still good and it corrects up to the distance and has good performance for these codes. And its maximum likelihood decoding, of course, isn't efficient. So now, confusingly, although it's called the minimum weight perfect matching decoder, it doesn't actually solve the minimum weight perfect matching in the detector graph. It solves what we sort of call the minimum weight embedded matching problem in the detector graph. So that's the set of edges of minimum total weight such that each detection event is incident to an odd number of edges, and the remaining nodes are incident to an even number of edges. And so this embedded matching problem under a different name, like a minimum weight T-join, has arisen in graph theory literature before as like a subroutine in the Chinese postman problem. And it's known that it can be solved, as I'll explain, by reduction to the minimum weight perfect matching problem, hence the name of the decoder. But the distinction isn't kind of important for this kind of whole project and the differences between different like implementations. So I'm sort of emphasizing it here. But yeah, so it can be solved by reduction to the minimum weight perfect matching problem, but it's not actually a minimum weight perfect matching problem. So what is minimum weight perfect matching? A perfect matching is a set of edges in some graph G such that every node in G is incident to exactly one edge in M. And then a minimum weight perfect matching is a perfect matching where the sum of the weights of the edges is minimized. And this can be solved by Edmonds' Blossom algorithm, as I'll explain shortly. So what's the reduction? So many here have probably implemented this themselves at some point. But the way you can solve this embedded matching problem, so if you start on the left with your sort of detector graph and your detection events, you first construct this complete graph on the detection events, where there's an edge between every pair of detection events in this graph corresponding to the minimum weight path between them. So the weight of an edge between two nodes in this path graph in the middle corresponds to the length of the shortest path between the nodes. And then if you run Blossom algorithm, for example, to solve find the minimum weight perfect matching in this graph, you obtain some set of paths or edges corresponding to paths, and then the edges in those paths correspond to the embedded matching. So that's the reduction. And so a common approach to implementing a matching decoder is just to do this sequentially. So you just construct this complete graph and solve the matching problem. But this is very slow. So firstly, it leads to a quadratic overhead in the expected runtime, just constructing this huge complete graph. So it's completely impractical for real-time decoding. And so when I wrote version 1 of PyMatching at the beginning of my PhD for my research, so I made some optimizations by kind of truncating this complete graph, which is much faster than solving the full problem sequentially, but it does introduce an approximation, and it's still sort of the speed is still very far from optimal. So as you'll see. So one key insight to improve the performance of the decoder is to implement the Blossom algorithm directly on the detector graph. And so in this work by Austin Fowler, it was shown that the sort of Dijkstra search step can be performed adaptively during the Blossom algorithm. So you sort of define some initial exploration radius for each detection event in this Dijkstra search stage, and sort of expand this region as required by the algorithm. But it's still kind of alternating between the sort of constructing sort of locally this sort of path graph and solving the Blossom problem. So it's still kind of a bit sequential, but it's adaptive. So it's got much better performance. And so our approach is conceptually similar in the sense we're implementing on the detector graph directly, but differs in many of the details as I'll explain. Okay, so our approach, in our approach, we sort of never construct this path graph, this complete graph explicitly. So the edges in the graph are sort of discovered by this Sparse Blossom algorithm exactly when they're needed and sort of forgotten when they're not. There's no separate Dijkstra search stage. So the path graph edges are never stored or found, or if they're not needed by Blossom. And so kind of you can think of it as adapting the Blossom algorithm to the differences between the perfect matching problem and the embedded matching problem, where you have these sort of 4 differences. You've got an embedding, so you're only matching some subset of the nodes. You're matching the parity of the nodes and not sort of enforcing one edge being incident to a node. We have a boundary where error mechanisms flip sort of one edge, one detector rather than 2. And also, very importantly, for the sort of the practical sort of runtime of the decoder, the expected runtime, the distribution of the problems that we might encounter in error correction are very different to what you might encounter in general for some perfect matching problem. In that we expect sort of the size of clusters, the probability of seeing some cluster to decay exponentially in its size for low error rates. Okay, so now let's give an overview of the Blossom algorithm. So the Blossom algorithm was discovered by Edmonds in 1965. And it was the first polynomial time algorithm for finding perfect matchings in graphs. And Edmonds also generalized it to finding minimum weight perfect matchings. And it finds perfect matchings through a search for augmenting paths. So what is an augmenting path? So an augmenting path is a path between unmatched and matched nodes. So you can, by an unmatched node, I just mean a node that's not incident to a matched edge in the graph. And so it alternates between sort of an unmatched edge and a matched edge. And so these are this is a path within the graph. If you augment an augmenting path, it increases the cardinality of the matching. So suppose you found some augmenting path. If you just take every unmatched edge and make it matched and vice versa, you've now got one more matched edge in your matching. And by Burgess' theorem, a matching is maximum, the cardinality is maximum if there is no augmenting path. So this kind of motivates the idea behind the Blossom algorithm, the unweighted Blossom algorithm. So the high level idea is that you find an augmenting path in the graph, you then augment it, and then you repeat. So the problem is, how do you find these augmenting paths? And the solution is to grow and merge what are called alternating trees. So what is an alternating tree? So an alternating tree is a tree subgraph of the full graph that alternates between matched and unmatched edges. So as I say, it's like a subgraph. And again, the dashed lines here are unmatched. So I should have said that before, I think it's labeled. Yeah, dashed lines are unmatched and the solid lines are matched. And it has this structure. And so for every unmatched node, you have some alternating tree. So at the beginning of the algorithm, every unmatched node is just a trivial alternating tree, just a root node. And then throughout the algorithm, you're kind of growing these alternating trees and finding sort of and growing that. You grow them by adding matches to them. I'll explain. And so when two different alternating trees connect, so you're exploring the graph and growing these alternating trees according to this, while maintaining their structure. And when two of them connect, then this green path between the two roots of the alternating trees is an augmenting path. And so we can augment it and increase the cardinality of the matching. So this is the process by which you find the augmenting paths. And so then you repeat this process with handling some important special cases until you find a perfect matching. And I'll explain the special case. The special cases are blossoms, the name of the algorithm. In particular, what can happen is, as I'll explain later, you can form odd lengths. So if, for example, you join these two nodes, you'd have an odd length cycle. And it's not clear how to handle these without being sort of very careful. So if you search the wrong way around an odd length cycle for an augmenting path, then you won't find the augmenting path. And so to handle this case correctly is kind of the, I guess, one of the key insights of Edmonds. Okay, so I've explained, so given a high-level picture of how you find a perfect matching using the Blossom algorithm, but then Edmonds also generalized this to find minimum weight perfect matchings. And this is motivated by, so what Edmonds did was formulate the matching problem as a linear program. And so this provides constraints for how the alternating trees can grow. And so these constraints are the constraints of so yeah.
Do you start at every node, or I mean, how do you start?
Yes, every possible node, yeah. Yeah, so every unmatched node. So initially, just every node in the perfect matching problem is just a root of a trivial kind of alternating tree. Okay. So yeah, so Edmonds formulated this as a minimum. The problem is a linear program. And so yeah, this provides some constraints for how the alternating tree can grow. And so for those familiar with linear programs, you have like a primal and a dual program, for primal and a dual problem. And the constraints of this dual problem and what are called the complementary slackness conditions. Actually, I've got in the appendix and slides on this. I probably had time to put them in, but I'm happy to come back to this to explain it in more detail. But the constraints of this linear program provide constraints on how these alternating trees can grow. And so by this, what's called the strong duality theorem of linear programming, this guarantees optimality once a perfect matching is found. Yeah.
You're talking about equality constraints there or inequality?
Inequality constraints. Well, if inequality constraints is a dual linear program, the complementary slackness conditions provide equality constraints. Yeah. And so, yeah, the linear program provides motivation for the Blossom algorithm, and also it's proof of optimality. But it's actually not required for either of those. It's motivation, but not required. You can sort of prove its optimality independently, and also the algorithms that require it. But it's still useful, especially for the terminology for the linear, the terminology from sort of formulating its linear program is useful to describe the algorithm. For example, these kind of dual variables and slack, which I'll define now. Okay, so what are dual variables and slack and tight edges? So a dual variable is defined for every node and for every odd size set of nodes in the graph. And so it's called a dual variable because it's a variable in this dual linear program. But as I say, we don't need to, that's not quite required to understand the algorithm. These variables are, so they're just real numbers, but they're always non-negative when Blossom is applied to the path graph. So because of the structure of the problem we're applying it to, they're always non-negative. And so as a result, we can visualize them as kind of the radius of some region centered on a node, or some odd size set of nodes. And you'll see why I'm doing this later on when we look at Sparse Blossom. And so, yeah, an edge is tight if its slack is 0. So what's the slack? So if you consider, say, some node and we've got some dual variable, and we're just saying the radius of this region here is just a dual variable, it's just this non-negative real number. And we can also have variables for odd size set of nodes. So this is 3 nodes. And the slack is the difference between the weight of the edge and kind of the sum of the dual variables associated with a node. So this is the slack. And if this slack is 0, then we say this edge is tight. So when you're visualizing it like this, it's as if these two regions are touching. And yeah, as you'll see why I'm using regions in a minute. Okay. So then now, so adding these constraints, effectively, the weighted Blossom algorithm is like the unweighted algorithm, but now with these constraints added, so these trees are now only allowed for tight edges, essentially these touching regions here. And so the way you grow a tree is you update these dual variables while still satisfying the constraints that you have to ensure are always satisfied so that you have an optimal solution. And so that's the way you do that. So suppose you want to sort of grow this tree or have it and explore the graph, you alternate between growing and shrinking regions. So the blue ones here are growing, or I say region, it's just you're just increasing the value of the dual variable. The red regions are shrinking, you're decreasing the value of the dual variable. And you increment them by the same amount so that they're always remaining exactly touching these regions, but then you can explore the graph. And then the idea here is that when these are growing, another edge outside the alternating tree will eventually become tight. And that tight edge can be used to either grow the alternating tree or collide with another alternating tree and find an augmenting path. And I've already said, yeah, that this can ensure the optimality. Okay, so that's the original Blossom algorithm. So then what's the difference with Sparse Blossom? So in Sparse Blossom, the concepts are similar, but they're generalized or they're sort of varied for the particular problem we're looking at. So now a dual variable is not just a real number, it does literally correspond to an exploratory region in a detector graph. So here, so for example, this is an example of what we call a graph fill region, or just, might occasionally just say a region. And so the radius of this region kind of corresponds to what was previously just a dual variable. And so now one of these, this kind of edge here is kind of corresponds to a shortest path between these two detection events. And this edge, which we call a compressed edge, is tight if these two exploratory regions in the graph are touching. So this background grid here is a detector graph. So each of these is like a different detector node. And then the yellow stars are the detection events. And so, yeah, so I just summarized in the table here. So each dual variable in the original Blossom algorithm is the radius of this exploratory region in its Sparse Blossom. Increasing a dual variable corresponds to sort of literally growing this exploratory region in the graph, sort of uniformly. Decreasing the value of a dual variable in the original Blossom algorithm corresponds to shrinking an exploratory region in the detector graph. And then any edge in the alternating tree or blossoms, which I'll define in a bit, in the original Blossom algorithm correspond to what we call compressed edges in the Sparse Blossom algorithm. And these represent the shortest path between detection events. And so the algorithm sort of proceeds along a timeline. It's kind of event-driven. So all the growing regions, the blue ones correspond, they grow with sort of 1 unit distance per time unit. Shrinking regions shrink with 1 distance unit per time unit. And then matched regions are frozen. So I say there's a kind of a distinction. You can think of, we treat the kind of these edges, these solid edges in the alternating trees as kind of tentative matches. So they're kind of distinct from what I just say as a match. So when regions match, they kind of become frozen. And then the alternating trees kind of have these tentative matches and unmatched edges. And these are either growing if they're blue or shrinking if they're red, and then frozen if they're matched. So when regions become matched, then kind of they're frozen. Yeah.
Is the difference between unified and this shrinking?
Yeah, there are a few. Yeah, I have a slide on that later on actually. So yeah, but that's one of the differences. Yeah.
What times it's matched so it can be frozen when the other one?
So the way that these two could become matched, for example, is that they were both originally unmatched detection events and roots of trivial alternating trees. These two trivial alternating trees collided, forming an augmenting path, and then you augment it, so it becomes matched. And at that point, it's matched. Yes, that's an example of a similarity. Yeah. But yeah, I guess the difference is there are more rules, there are more cases, there are more differences, and you're guaranteed to have a minimum weight solution here, whereas union find will be sort of generally low weight. Yeah, so there are similarities. Yeah, the difference is in kind of there's only the solution weight is optimal in the matching case, but not in the union find case. And the data structures are more complicated in Blossom, but the expected running time is the same. And yeah. Yeah, so initially, so you initialize all detection events start out as the roots of these kind of growing regions, roots of these trivial trees. And as the alternating trees grow, so there are various what we call sort of matcher events, sort of high level kind of events that can occur and be processed. And these just, before I explain them, I mean, there are many different events that can occur. As a region is growing, it's kind of growing into empty nodes, and shrinking, it leaves empty nodes. But I'll now explain kind of the high level events that can occur involving different regions colliding and alternating trees growing and matching. So yeah, so two alternating trees can grow and collide. An alternating tree can hit itself, forming a blossom, which I'll finally define soon. A blossom can shatter. That's another difference with union find. And once you kind of process all these events and everything is handled, eventually all the regions will become frozen when they're all matched. But some blossoms may remain, and at that point you may have blossoms, which I'll define, matched to other blossoms, and you have to sort of shatter these, as I'll explain. So I'll just go through kind of the 3 or 4 key sort of, I think 4 of the key things that can happen, and there are 3 other kind of edge cases which I can talk about, the sort of details at the end if needed. So yeah, this is what I kind of already explained in the case of the regular Blossom algorithm. So when these 2 different trees grow, these are now exploratory regions. I've omitted the kind of the background detector graph, but from now on, always assume that these are now graphil regions and these are detection events, and the detector nodes are just not shown. But yeah, when these 2 different trees, these are now growing regions, so they can collide in the graph. So these 2 growing graphil regions collide, and at this point, you're essentially augmenting this path, so you can invert this. This becomes matched, this becomes unmatched, and they become frozen. There's no longer any unmatched node here, so they don't need to grow. They're just frozen regions. So yeah, you sort of shatter the tree into matches and freeze the regions. They stop growing. And this increases the cardinality of the matching by 1. Another thing that can happen is, so the way that these alternating trees, they start out as these trivial just root nodes, but they can grow because one of these nodes can hit like just a matched pair of regions. And if this happens, the match and its match get added to the alternating tree. So this region starts shrinking and this region starts growing. And so you've now got a larger alternating tree. Another thing that can happen is an alternating tree can hit itself. So you imagine you've got these different regions growing. If a tree collides with itself rather than another tree, you've now formed this odd length cycle. And now this forms what's called a blossom. And this blossom itself now starts growing. It's just treated as like a pseudo region, like a pseudo node. It's just like itself is just a region in this alternating tree. And the internal structure is now not relevant to these kind of until it shatters, the internal structure is no longer kind of relevant to the growth of the alternating tree and how it collides. So yeah, this radius here is kind of how much the blossom has grown on the outside. And again, this would correspond to a variable in the original blossom algorithm. It corresponds to a variable of an odd size set of nodes in this dual linear program. And so yeah, you've got this kind of loop and it kind of turns around at the most recent common ancestor, and this loop forms a blossom, like a virtual region. So what's a blossom? So the radius of a blossom is like the distance it has grown since it's formed. And blossoms can be nested, they're recursive. So this is an example of a blossom containing 3 regions, one of which is itself a blossom. So it's a recursive data structure. And we say that the regions inside the blossom are called its blossom children. Now, a blossom can also become a shrinking region. And if it becomes a shrinking region, its radius can shrink to 0. And at that point, it can shatter. And so the even length path through the blossom becomes matches, and the odd length path is added back into the alternating tree like this.
Sorry, can you say something about how in general anything becomes a shrinking region?
Yes. Yeah. So this here could have been a blossom. It could have matched, and then some other growing region could have come along and collided with it. And that would now be added to an alternating tree and it becomes a shrinking region.
So the rules are that on an alternating tree, they alternate growing.
Yes.
Shrinking.
So that they're always tight. The edges are always tight.
But at the beginning, everything is a growing node.
Yes.
So like frequently I'm going to get 2 growing nodes touch each other. How do I determine which one is now shrinking?
So when the 2 nodes touch each other, they'll just match and they'll freeze. But then when this region hits this matched region here, this one, the closer one, becomes a shrinking region, so that this stays tight. Like if this is growing, this has to be shrinking at exactly the same rate, so that this kind of compressed edge is a tight edge. So this is the shrinking region, and this is the growing region. Yeah, there'll only be one choice that allows that. Maybe there's some degeneracies, but yeah.
You know, I feel like at the beginning.
Yeah, and either valid one is, yeah, there are times when 2 events, so this is a thing we had to be very careful with the implementation, is that many things can occur at exactly the same time, so you have to assume that everything can happen at the same time. So you have to make sure that everything, yeah, every time there are kind of invariants of the algorithm that have to be satisfied all the time to ensure that any choice you make is valid. But yeah, they're kind of unlikely. In general, everything will happen at different times, but not in general, but typically. But yeah, it still works if they happen at the same time. Yeah, you just have to pick either. It's just either valid choice is perfectly fine. Yeah. So yeah, so if that became a shrinking region, it can shatter, and that's what you do if that happens. And so I've explained the left 4. I won't explain these right 3 now, but I can come back to them if needed. But basically, you have to handle the boundaries and a trivial region shrinking. But the key points are on the left side there. And as I say, eventually at the end of the algorithm, it may be that you have these blossoms which are matched rather than just trivial regions. But there's always a unique way to shatter these blossoms into matches correctly, such that you have a sort of minimum weight matching. And actually, these regions that you have at the end, they provide proof of optimality. These corresponds to this dual linear program. And as I said, if you're familiar with that, then it kind of provides a proof. You can provide this, and you don't have to solve the Blossom algorithm again. It's provided proof that you found the optimal solution. Okay, so I'll kind of explain, in order to give a bit of an idea of how the algorithm works, and also some of the kind of the most important optimizations to make it fast. I'll give kind of an idea of how you can think of it at a high level in architecture. So we kind of have these 4 different components, like a tracker, a floodder, a matcher, and a driver. So the tracker is essentially responsible for the timeline. Actually, I'll start with the driver maybe. So the driver is responsible for kind of interfacing with the outside. It takes in the decoding problem, prepares the problem state, interprets the solution, and gives it to the matcher. The matcher is responsible to these high-level concepts, like the collisions of alternating trees, blossoms shattering and forming, matches matching, regions becoming matched, and also whether or not regions should be growing or shrinking, kind of making that decision. The floodder knows nothing about that. The floodder only cares about the fact that how to grow and shrink the regions. It's told that it should have a growing region, and it adds sort of empty nodes to this region as required at the right time, and shrinks them, and notices when 2 regions are colliding without knowing at a high level what that means. And it uses the tracker, which is essentially like a kind of an optimized priority queue. And so this is responsible for the timeline and scheduling events, both these kind of fine-grained events and the high level. Well, yeah, the fine-grained events for the floodder, so collisions, regions colliding. And so you can imagine, so you might give some detection events to the matcher, tells the floodder to kind of run until something interesting happens. The floodder sort of maybe the floodder will look at some node and look at the neighbors of some node, see some potential events, and then ask the tracker to remind it to look back, say at node 5 at time 3. The tracker will then give the reminder to look back at node 5 at time 3, and the floodder will notice that there's a collision between 2 regions, say region 5 and region 6. The floodder tells the matcher, which will then notice that maybe these are 2 sort of separate alternating trees and they should match, and decides how they match, updates the region growth rates, and then informs the floodder, and so on. And eventually, when there are no more events, that's because all the matches, everything has become matched, so everything is frozen. So there are no more events that can happen. And that's when there's this final state, which is given back to the driver, which outputs the logical observables that were predicted by the decoder. So yeah, I'll just a couple of the key kind of optimizations that were important for getting to be fast. So one is the tracker. So I guess you can think of these like the inner loops on the left here. So the most important ones to optimize are these 2. So I'll just go over the tracker and the floodder. Firstly, we use a priority called a radix heap. I won't go into the details, but can talk about it if needed. It's like a very fast monotone priority queue. So it uses the fact that events are always in monotonically increasing time. And that, along with the fact that we have kind of sort of say 32-bit integer weights, means we can use this very fast priority queue that has sort of constant complexity or order B complexity, where B is the number of bits in the edge weights. So that was kind of very important for speed. And also, we don't actually put all the events in the priority queue. So we use some tricks. We only have a sort of in queue the next event that's going to occur. And this is important sort of preventing kind of what we call sort of chaff. So if 2 regions were going to collide, but then one started shrinking or they matched, there are many, many events that were just never going to occur. And so you don't need to put all of them in the priority queue. So we only ever queue sort of the next event at some node or graph or region that's going to occur, and then come back to enqueue the next one. One sort of simple optimization that's kind of very useful is that the detector nodes in a region are stored as a stack. And that means that although there's a difference between Unify and a Blossom, one of the differences is that you can have these shrinking regions. But shrinking a region is extremely cheap because you don't need to iterate over the nodes to shrink a region. Because we store all the nodes as a stack, you just look at the top of the stack, see what pops off next, and schedule that, enqueue that event. Now, one optimization that also applies to union find, as I'll explain in a minute, is compressed tracking. So we don't track the exact path used to reach some node. We don't sort of track the edges in that path. We only track the logical observables that were crossed to reach it, and the detection event it was reached from. And the logical observable mask, this is just like a bit mask representing which logical observables are crossed by some path, is local information at the point of collision. So if you have these 2 growing regions, and I kind of just, the red here is now just because, yeah, forget the coloring that you saw before just for this slide. So you have 2 growing regions, and this is what corresponds to, say, some logical observables, say some logical X observable in a surface code. And as this region is growing, when it crosses the logical observable, all the detector nodes in this region have stored in a bit mask which logical observable is being crossed, so that is crossed logical observable. And at the point of collision, you discover this sort of compressed edge representing the shortest path, but what you store is not the edges in the path, but just the logical observables crossed by the path. And so actually that means you've only got a constant amount of information to represent any path in the graph, no matter what its size is. And then as well as the logical observable, we also track the endpoints, which is very important for shattering blossoms. So each node stores a detection event it was reached from. And so these, this is a Voronoi style diagram here. And so each color here is just representing kind of the detector node that this part of the region was reached from. So red here means that this was reached from this detection event. And so when these two regions collide, we sort of know which detection event it was reached from. So again, that's stored in this compressed edge and is crucial for shattering blossoms correctly. And again, it's sort of known from local information at the point of collision, and we don't have to store the actual paths themselves. So yeah, so it uses a constant amount of data to represent any path. And so yeah, for surface codes, it's just a single bit, right? You can then apply the same ideas to union find. So I won't go into the details. So for those who are familiar with union find, maybe this slide will make sense. For those not, possibly not. But I can go into this more detail at the end if needed. So you can use this compressed tracking to provide a kind of compressed representation of cluster trees in this sort of disjoint set union data structure. So rather than kind of normally you'd have this sort of disjoint set data structure to represent every sort of node in some cluster in union find. Instead, you can just represent this compressed representation of paths between detection events rather than detector nodes in the cluster tree. And then during this sort of path compression step, which will be familiar to some of you of union find, you can just keep track of these observable masks. They're just these are just XOR. These are very efficient operations because they're just XORing some bit mask. And so this completely eliminates the need to construct a spanning tree in union find. And so the compressed cluster tree is already a tree. And so if you're familiar with peeling, which is the step of union find, you can just peel this compressed cluster tree. So it's like it's a compressed representation of the tree. And so it's a smaller tree than you normally have in union find. And also you can just peel that directly. You never have to construct some spanning tree in the graph. So I've already made a couple of questions on this. But yeah, there are some sort of similar. You may have noticed some similarities between Blossom and union find. It's also shown in this recent paper by UA and others. So you can think of union find as like an approximation, first shown in this paper here. Union find was viewed as an approximation of Blossom. And so both algorithms involve kind of growing exploratory regions, but in Blossom, the regions can also shrink. In union find, the clusters only ever merge, but they never split, whereas in matching, the blossoms can shatter. In this paper, they showed that sort of in some cases, such as repetitions codes, where kind of such as the XZX code at infinite bias, the two algorithms provide identical solutions. But of course, in general, matching will provide a more optimal solution. And also, yeah, so UA, his Shruti students, recently released Fusion Blossom, which is kind of very impressive independent work, which is sort of conceptually similar to what we did. So the differences are that it also implements sort of Blossom directly on the detector graph, so conceptually very similar. Fusion Blossom kind of grows clusters. My understanding is it grows clusters more as done in union find, whereas kind of we have this sort of timeline concept and use priority queue. But Fusion Blossom also adds parallel execution. So we don't have any parallel execution. Ours is a serial implementation, although we have faster single core performance. But definitely check out Fusion Blossom, and I believe a paper is coming soon. Okay. So below threshold, so at small p, the errors form clusters, very small clusters, which can all be matched independently. So if you if you're looking at how I've sort of described the algorithm, you can see that if you imagine you just sort of highlighted every edge or node in the graph that was touched by the Sparse Blossom at any point in the algorithm, they would form kind of separate connected components. And these separate connected components, the size of them would kind of, the probability of seeing some components of some size is sort of exponential in its size for small p. So if we assume that the probability that some node is contained in some cluster where I define clusters I just did, not an union find, so some region that was explored by Sparse Blossom, then the probability of that a node is contained in some cluster of size n is exponentially small in n. And then the worst case running time of the whole algorithm is n to the 4. So the expected time per node is constant. And so the expected running time is linear in the number of nodes. And actually, almost all the time, it's just sort of 1 to 2. I'll show in a minute some statistics, but typically the blossoms are extremely small or trivial. And so, for example, this is at 0.3% circuit level noise for distance 11, and these are the number of nodes in some alternating tree. And almost all the time, it's just sort of one or two or three nodes, and the number of nodes in some alternating tree decays exponentially in its size. Oh, whoops. Okay, so I already showed this at the beginning of the talk, but yeah, so 100,000 times faster than network X and 1,000 times faster than the original version. And so at distance 30, the decoding time is sort of less than 5 microseconds per round. Ideally, we want that to be, say, less than a microsecond. So there's more work to be done, say, in parallelization to sort of achieve that benchmark. And then roughly linear, so you can see the complexity is sort of almost linear in the number of nodes n, as expected. This is at 0.1% circuit level noise. We'd expect it to be linear. But even above threshold, so at 1%, so threshold, say 0.7%, even sort of well above threshold, the runtime is still good and a lot faster than before and sort of close to linear in runtime, even at very high error rates. So yeah, in conclusion, we've introduced Sparse Blossom, which is a variant of the Blossom algorithm tailored to error correction. And the key improvement is the fact that we sort of never construct this path graph and we only discover it as needed, so it's never stored. So it kind of eliminates this quadratic overhead. The throughput matches that of a superconducting quantum computer at a distance 17. It's open source, so and it integrates well with STIM. So I definitely recommend, if you haven't already, trying out STIM. So it's a very quick way of running kind of large scale error correction simulations. So future directions. One is to kind of handle hyperedges. So by implementing, say, a belief matching decoder, so Sparse Blossom can be used as a subroutine in this decoder to handle kind of correlated errors. I've said that so far one of the approximations is that all the error mechanisms flip 1 or 2 detector nodes, or cause 1 or 2 detection events. But in general, they could cause 3 or 4, say, in the surface code. So including that information can be done using Sparse Blossom as a subroutine. Also adding support for parallelization by sort of combining ideas from Yue's work on Fusion Blossom, sort of with our work, would be another way to improve would be one way to improve the speed further. And implementing it as a streaming decoder would be important. So what I've described is like a batch decoder. It takes in some decoding graph and a batch of syndrome data, then decodes it and returns a solution. Ideally, you want to have a stream of data and be able to process that. And also into implementing hardware would be, as we go to say, for example, FPGA implementation. And yeah, that's it. So thank you.
Any questions? So one of the things you mentioned about you have this operator that you need to know. So when the interface for using it, is you pass in, you have to pass in the Detector and the logic.
Yeah, the interface is at each edge. You assign some set of logical observables that are flipped. You can actually just give it just a unique observable for every edge. What I've described was kind of if you assume you have, say, some constant number of observables, say 64, and you have some 64-bit bit mask to represent it. If some details are that if you can provide as many as you want, and we handle the case as well. You can post-process the solution with some Dijkstra searches for a small overhead to also get the case for more than 64 observables as well. But yeah, the interface is you just assign, you provide like the observables that are flipped for each edge, which could just be unique for each edge, or it could just be some small subset correspond to, say, some logical observable.
So the other thing you mentioned, like faster rate than human time. So can you use it to do time without maybe even want to do it faster?
Yeah, you could adapt the
That's good. Thanks for a great talk. I didn't quite get the difference between MWEM perfect matching and MWEM.
Yes, I'll just go back to the Might be easiest if I just get back here. Yeah, so in the original Blossom algorithm, which solves the minimum weight perfect matching problem, every node in the detector graph has to be incident to exactly one edge. So every node has to be incident to exactly one edge. In an embedded matching, you're enforcing odd parity on some subset of the nodes, the detection events. So it's like a different problem. So firstly, you're only interested in some sense, you're enforcing some subset of the nodes having this odd parity. You're enforcing odd parity rather than exactly one edge incident to the node. So it's parity rather than exactly one. The other difference is you have a boundary in the decoding case. And then the other one, which is just the specifics to error correction as well, with the boundary is a distribution, is kind of exponentially distributed. So these are the key differences between the perfect matching problem, say solved by Blossom, Edmonds algorithm, and say Blossom 5, and then the embedded matching. There are these differences, and so you can think of it as we're adapting the Blossom algorithm to these differences. Yeah, does that make sense, or is there?
Thanks.